Nearly 10,000 light-years away in the constellation of Scutum, a crimson giant burns with a fury so vast that even trying to comprehend its scale bends the limits of imagination. This is UY Scuti, the largest known star in the Milky Way, and standing it beside our Sun is like placing a basketball next to a grain of sand. If it were to replace our Sun at the center of the solar system, Earth, Mars, and the entire asteroid belt would be swallowed whole, suspended inside an ocean of boiling plasma that stretches more than 1,700 times wider than our own star. To call this a star is almost an insult. It is a living monster, a cosmic leviathan, a celestial furnace so incomprehensibly huge that it feels less like part of the universe and more like the universe itself. But its size is not the most terrifying thing about it. The real horror of UY Scuti lies in the fact that it is dying, and when giants like this perish, they do not fade quietly into the dark. They explode with a violence that defies words, a cataclysm so powerful that it outshines entire galaxies and scatters the raw ingredients of life across the stars. Imagine for a moment the sheer fragility of our world. The Sun, steady and calm, has burned for over 4.5 billion years and will continue to shine for billions more. Its slow, methodical pace allows life to evolve, civilizations to rise, and futures to unfold. But UY Scuti is a sprinter, not a marathon runner. In less than 10 million years, it has already devoured nearly all of its fuel, living fast and burning bright in a reckless race toward oblivion. Where our Sun will calmly age, UY Scuti is already pulsing with instability, breathing in and out with a heartbeat that takes years to complete, its massive body expanding and contracting across distances that would take light more than 8 minutes to cross. It is not a stable giant, but a balloon, stretched thin, trembling on the edge of collapse, and collapse it will. Deep in its core, nuclear fusion has moved far beyond the gentle burning of hydrogen that powers ordinary stars. UY Scuti now fuses heavier and heavier elements in a desperate attempt to stave off its inevitable fate, burning helium into carbon, carbon into oxygen, oxygen into silicon, each stage faster, hotter, and more unstable than the last. But physics is cruel. Once it produces iron, the game ends. Iron cannot fuse to release energy, and when that moment arrives, gravity, patient, eternal, undefeated, will finally crush the giant in on itself. In less than a second, the core of this monster, once larger than Earth itself, will collapse into a ball only a dozen miles wide. The rebound will generate a shockwave more violent than anything the galaxy has seen in millions of years, and the explosion will shine brighter than 5 billion suns. For a brief period, this single star will outshine the entire Milky Way. We are far enough away to be safe when it happens, but the spectacle will be visible from Earth even in daylight. Shadows will stretch across the ground, cast not by the sun, but by the violent death of a star thousands of light years away, and when the glow fades, the story will not end. The remnants of UY Scuti will leave behind either a spinning neutron star or, if its core is massive enough, a black hole, an object so extreme that time itself stops at its edge. But before that happens, it will scatter the universe with treasures, gold, silver, platinum, uranium, all forged in the nuclear chaos of its death, the same elements that built our planets, filled our oceans, and formed the blood and bones inside your body. In a way, UY Scuti is not just a monster. It is an ancestor. Its eventual death will write the future of countless worlds. So tonight, when you look up at the stars and see the tiny glimmers scattered across the sky, remember this. One of those points of light is a red supergiant waiting to die. Its end will be a spectacle across the galaxy, a funeral pyre that will echo for millions of years. This is the story of UY Scuti, the largest star we know, and its terrifying countdown to destruction. When astronomers first measured UY Scuti, they were confronted with something that almost defied comprehension. Here was a star so immense that comparing it to our sun felt ridiculous, like trying to measure a mountain against a pebble. UY Scuti resides in the constellation of Scutum, nearly 9,500 light-years away, yet even across that gulf of distance, its presence dominates. It is classified as a red supergiant, but supergiant doesn't come close to capturing the scale. This is a star 1,700 times wider than the Sun, so massive in appearance that if you placed it where our Sun sits, its fiery atmosphere would stretch out past Mars and deep into the asteroid belt. The sheer size alone is mind-bending. Imagine the solar system as you know it. Mercury, Venus, Earth, Mars, all swallowed whole, their orbits consumed by a star that would leave only Jupiter clinging to the edge of its enormous glowing surface. To stand anywhere near such a star is not even possible. The concept of surface barely applies. Instead, its outer layers are a swirling sea of plasma, bubbling, boiling, and surging outward across distances so vast that light itself takes nearly 2 hours to cross from one edge to the other. But here's where the mystery deepens. For all its unimaginable size, UY Scuti is not especially massive. While it stretches more than 1,000 times wider than the Sun, it weighs only about 30 times more. This strange relationship makes it more like a cosmic bubble than a solid sphere. Picture an enormous balloon inflated to the size of a stadium, but filled with air, so thin that it weighs less than you expect. That is UY Scuti, vast, swollen, and delicate in structure compared to its intimidating appearance. This imbalance between size and mass makes it one of the puffiest stars ever discovered, and that puffiness is the key to its instability. Unlike compact stars, whose gravity holds them tightly together, UY Scuti's outer layers are barely tethered to its core, drifting outward in massive convective currents that give the star a heartbeat. Every 740 days, UY Scuti pulses. It expands and contracts rhythmically, its outer envelope breathing like a living creature on a cosmic scale. When it expands, it grows so large that its volume would dwarf anything we can imagine. When it contracts, it shrinks slightly, but always remains staggeringly huge. These pulsations are not gentle. They carry entire layers of plasma outward, releasing massive amounts of energy and gas into surrounding space. Astronomers have watched as UY Scuti sheds its skin, expelling dust and matter that form enormous clouds around it, veiling its light and making it even harder to observe. In fact, one reason UY Scuti remained relatively unknown until recent decades is that it is cloaked in a dusty shroud of its own making, dimmed and distorted by the haze of material it has blown into the cosmos. If we could replace the Sun with UY Scuti tomorrow, the consequences would be immediate and devastating. Earth, Mars, and everything in between would be gone, engulfed by stellar plasma thousands of degrees hotter than any forge ever conceived by humans. Even Jupiter, orbiting at 500 million miles away, would skim dangerously close to the star's outer atmosphere. Imagine standing on Earth and seeing not a distant glowing sun in the sky, but a horizon dominated entirely by a wall of fire. Day and night would vanish, because there would be no escaping the glare of a star that filled the heavens. This is the scale of UY Scuti, a star so enormous that it rewrites our very concept of size and distance. Yet, this grandeur hides something deeply sinister. Its vastness is not a sign of strength, but of weakness. Stars like UY Scuti swell to such sizes only when they are nearing their end, when their cores are burning through heavier elements in a desperate attempt to stave off collapse. Its giant, balloon-like body is a symptom of instability, the death throes of a star burning itself apart. Every pulse, every expansion, Every cloud of dust it ejects is a reminder that UY Scuti is running out of time. Astronomers who gaze at this swollen red giant are not just witnessing the majesty of the largest known star. They are watching a countdown clock tick closer to zero, a cosmic leviathan trembling on the edge of destruction. For our sun, life is a steady and methodical journey. It has burned hydrogen for over 4.5 billion years, and it still has another 5 billion left before it reaches its end. That calm, dependable pace is the reason life on Earth had time to emerge, evolve, and build civilizations. But UY Scuti is no patient marathoner. It is a sprinter, a reckless cosmic runner, burning through its fuel 1 million times faster than the sun. In just 10 million years, a blink in the cosmic scale, it has already exhausted most of its hydrogen and moved on to heavier and more desperate forms of nuclear fusion. That difference in time scale is staggering. If the sun is a steady candle that lights a room for the entire night, UY Scuti is a flare, brilliant, blinding, and gone before the night is even halfway over. This furious pace of energy production comes with consequences. Inside UY Scuti's core, fusion reactions are not just faster, they are chaotic and unstable. Hydrogen, the simplest and most abundant fuel in the universe, was consumed early in its life. As the hydrogen vanished, gravity began to win the ancient tug of war against radiation pressure, compressing the core and raising the temperature to levels that ignited helium fusion. But helium burns far more quickly than hydrogen, lasting only about 1 million years. Once helium is gone, the star contracts again, igniting carbon fusion. Each stage burns hotter, faster, and more violently than the one before it, like a furnace being stoked with larger and larger logs, until nothing remains but ash. What makes UY Scuti terrifying is not just its enormous size, but this desperate chain of fusion. While the sun has time to linger on each stage for billions of years, UY Scuti races through them, consuming its life in a frantic sprint toward death. Helium to carbon, carbon to oxygen, oxygen to silicon, each new element demands higher temperatures and pressures to fuse, and each stage lasts a fraction of the time of the last. By the time silicon fusion begins, the clock is measured not in millions of years, but in days, and when iron begins to form in the core, the star's fate is sealed, because iron cannot fuse into anything heavier without consuming more energy than it produces. At that point, the core becomes a dead weight, collapsing under the crushing pull of gravity in less than a second. From the outside, however, this furious struggle looks deceptively calm. UY Scuti's surface glows a dull red, cooler than our sun's yellow-white light. Its surface temperature is only about 3,000 degrees Celsius, making it appear like molten copper in the sky rather than a blinding beacon. This cooler glow is a lie. It hides the ferocity of the processes raging in the core, a quiet mask over a storm that is tearing the star apart from within. The red glow is not a sign of weakness, but a signal that the star has expanded to its greatest size, puffed up by the desperate fusion of heavy elements. It is the glow of a dying giant, its final embers glowing faintly before the inevitable collapse. If UY Scuti were placed in our solar system, Earth would already be long gone, swallowed whole by its massive atmosphere. The sheer heat and radiation released during its unstable phases would strip away atmospheres, boil oceans, and reduce planets to cinders. Mars would fare no better, and even the asteroid belt would dissolve inside the stellar plasma. Only Jupiter, orbiting just beyond the star's swollen surface, might survive, and even then, it would not be safe. The gravitational tides alone from a star this size could tear moons apart and destabilize entire planetary systems. It is no exaggeration to say that if UY Scuti lived where our sun does, life on Earth would have never existed in the first place. But the story of UY Scuti is not about what it could do to us. It is about what it is already doing to itself. Its puffed up body, its pulsing heartbeat, its shedding of material into space, all of it points to a star in its death phase. UY Scuti is no young and vigorous star. It is old by the standards of massive giants, and its life is measured not in billions of years, but in millions, maybe less. The countdown has already begun, and every pulse it emits into the cosmos is like the ticking of a cosmic clock running out of time. Deep inside UY Scuti, far beneath its swollen layers of red plasma, lies a nuclear furnace in its final and most desperate phase. For millions of years, this star has fought a constant battle between two titanic forces, gravity pulling inward and nuclear fusion pushing outward. As long as hydrogen remained in its core, fusion could hold back gravity with ease, releasing energy that pushed against the crushing weight of the star's enormous mass. But hydrogen does not last forever, especially when burned at 1,000,000 times the rate of our sun. UY Scuti tore through its hydrogen in a cosmic heartbeat, leaving its core depleted and forcing the next stage of its desperate survival. When the hydrogen was gone, gravity briefly gained the upper hand. The core collapsed inward, heating to extraordinary temperatures until helium fusion ignited. For a short while, balance returned, but helium burns much faster than hydrogen, and soon it too began to run out. The star was forced into a cycle of collapse and ignition, each stage shorter, hotter, and more unstable than the last. Helium fused into carbon, carbon into oxygen, oxygen into neon, and silicon. Each fusion stage was like a larger log being thrown into a dying fire, hotter, brighter, but consumed in less and less time. 1,000,000 years of helium burning, then only thousands of years of carbon, then hundreds for oxygen, and perhaps a single year of silicon burning. The timescales compressed to nothing. What once lasted millions of years now lasts only months or days. The star is burning through its final reserves in a frenzy, racing toward a fate it cannot escape. At the heart of this process lies a trap set by physics itself. When fusion produces elements lighter than iron, it releases energy, and that energy sustains the star against gravitational collapse. But when the core becomes iron, the rules change. Iron cannot fuse into heavier elements without consuming more energy than it gives back. Fusion halts, the outward push of energy disappears, and gravity finally has no opposition. This is the moment all massive stars dread. The iron core, silent and heavy, building with every passing second until the weight becomes unbearable. For UY Scuti, this moment will come in less than the blink of an eye compared to its long lifetime. A core the size of Earth will collapse in less than a single second, imploding under gravity's relentless pull. The physics of this collapse is nothing short of violent. As the iron core shrinks, protons and electrons are forced together into neutrons, releasing a flood of neutrinos that outnumber all the atoms in the universe. These ghostly particles normally pass through matter without interacting, but in the super-dense heart of UY Scuti, even they are trapped, creating a pressure that briefly halts the collapse. For a fraction of a second, the imploding core rebounds like a spring released, sending a shockwave racing outward through the star. But the outer layers are so massive and dense that the shockwave stalls halfway, threatening to collapse into failure. If nothing revives it, the entire star will simply vanish, consumed into a black hole without even the courtesy of an explosion. But neutrinos, those elusive messengers of the nuclear world, play their final trick. A small fraction of them finally interact with the collapsing matter, depositing just enough energy to reignite the shockwave. In that instant, the star's death becomes unavoidable and spectacular. The shockwave roars outward with unimaginable force, tearing through layer after layer of stellar matter, heating everything to hundreds of millions of degrees. Nuclear reactions ignite in the blast itself, forging elements that never existed before: gold, platinum, uranium, born in the chaos of destruction. Within seconds, the surface of the star is blasted outward and the explosion begins its rise to brilliance. For UY Scuti, this sequence is no longer theoretical. The elements in its atmosphere, the pulsations of its body, and its immense, unstable size all point to a star in its final nuclear stages. Somewhere in its heart, silicon fusion may already be underway, the last desperate fuel before iron seals its fate. The star is in its death spiral, and when the final collapse comes, it will happen with no warning. From the outside, UY Scuti may look calm, glowing faintly red in the constellation of Scutum, but beneath the surface, physics is sharpening its blade, preparing for the inevitable instant when gravity wins. And when that moment arrives, the entire galaxy will know it. When the final second of UY Scuti's life arrives, there will be no gentle transition, no fading glow that signals the end. Instead, everything will happen almost instantly, as though the star's colossal body finally caves under the unbearable weight of its own existence. At the heart of this giant, the iron core grows until it can no longer sustain itself, and gravity seizes its opportunity with brutal swiftness. What was once a sphere larger than Earth collapses in less than a heartbeat, shrinking to something only a dozen miles across. The crushing force is so intense that matter itself changes form. Protons and electrons fuse into neutrons, creating an object denser than anything we can comprehend. A single teaspoon of this matter would outweigh a mountain. In that moment, UY Scuti's core ceases to be an ordinary star and becomes the densest object in the known universe. But collapse is not a silent affair. The implosion of the core sends a shockwave surging outward, though at first even this seems doomed to fail. The outer layers of UY Scuti are so massive that they smother the initial burst, halting its progress as if the star is unwilling to let go of itself. For a moment it seems possible that the entire body of the star will simply fold in on itself, forming a black hole with no dramatic explosion, no brilliant finale, just a silent vanishing act, as though the largest star we know had been swallowed whole by its own gravity. But deep inside, another process is at work, one that ensures this ending will be anything but quiet. As the core collapses, it floods the star with neutrinos, tiny, ghost-like particles that pass through nearly everything but are produced in numbers so staggering that they carry away most of the collapsing energy. Normally, neutrinos would simply vanish into the cosmos unnoticed, but here inside UY Scuti's dying body, the density is so great that some of them finally interact with the surrounding matter. That small fraction is enough to change everything. The stalled shockwave roars back to life, reignited by the infusion of energy, and now it has the power to blast apart the star from the inside out. In less than a second, the reborn shockwave accelerates outward at unimaginable speeds, tearing through the star's layers like a cosmic wrecking ball. Hydrogen, helium, carbon, oxygen, and silicon, all the shells of fuel UY Scuti once burned, are ripped apart in a violent chain reaction. Temperatures soar to hundreds of millions of degrees, forging elements heavier than iron in the fiery chaos. Gold, platinum, uranium, and countless other heavy atoms that do not form in ordinary stellar furnaces are born here, in the explosive crucible of death. The star's outer layers, weighing many times the mass of the sun, are hurled into space at tens of thousands of miles per second. From the outside, this moment will appear as one of the most dramatic events the galaxy has seen in millions of years. The light from the explosion will surge across space until it reaches Earth, where it will shine brighter than 5 billion suns. For weeks, it will be visible in the daytime sky, casting shadows at noon and outshining every star in the night sky. Astronomers believe it will rival the brilliance of the full moon and linger for months, a constant reminder that somewhere in the Milky Way, a titan has fallen. Yet even this awe-inspiring detonation does not mark the end of UY Scuti's story. The material blasted outward will continue expanding, glowing with radioactive decay, lighting up the galaxy with its aftershocks for years. And at the center, hidden within the wreckage, the core will have transformed into something new, a neutron star spinning hundreds of times per second, or if the collapse overwhelms even that resistance, a black hole, an object so extreme that not even light can escape. The collapse is not simply destruction. It is creation through annihilation, a moment when matter is broken down and rebuilt in new forms, when the death of one giant becomes the seed for countless new worlds. But before the universe can recycle its ashes, it must first endure the explosion, the single most violent act UY Scuti will ever commit. When UY Scuti finally detonates, the galaxy will witness a firestorm unlike anything seen in millions of years. The reborn shockwave that rips through its swollen body will tear away every layer of the star, releasing more energy in a single instant than our sun will generate over its entire 10 billion year lifetime. This is no ordinary death. It is a supernova, one of the most violent spectacles the universe has to offer. From the very first moment, the explosion will outshine entire galaxies, producing a light show so brilliant that even from nearly 10,000 light-years away, it will dominate Earth's skies. For weeks and months, the night sky will host a new star brighter than Venus and nearly as luminous as the full moon, glowing with the incandescent fury of 5 billion suns. During its peak, shadows will stretch across the ground at noon, not from our sun, but from a star's death throes unfolding thousands of light-years away. At the heart of this cataclysm, the heat and violence of the explosion ignite nuclear reactions that forge the universe's rarest treasures. While stars like our sun can build elements up to oxygen, magnesium and silicon, it takes the unbelievable energies of a supernova to create gold, platinum, uranium and other heavy metals. These elements are not simply scattered, they are manufactured in the fire itself, born in the split-second chaos of atomic nuclei smashing together under conditions so extreme that they cannot exist anywhere else in the cosmos. In just a few seconds, UY Scuti will produce more gold than exists in Earth's entire crust. Every precious ring, every silver circuit, every uranium atom fueling reactors on Earth can trace its ancestry to explosions like this, to the violent deaths of stars that once burned across the Milky Way. The supernova does more than create, it destroys with equal ferocity. The outer layers of UY Scuti, weighing many times the mass of our sun, will be hurled into space at 20,000 kilometers per second. The blast will bulldoze through the interstellar medium, sweeping up dust and gas, compressing molecular clouds, and sparking new rounds of star formation. What was once a giant will be torn apart into fragments that ripple outward for light years, creating a glowing nebula that will expand for hundreds of thousands of years. These expanding shells of hot gas, called supernova remnants, are the grave markers of massive stars, but they are also cosmic cradles. In the wake of such destruction, entire generations of new stars will ignite, some with planets orbiting them, and perhaps on one of those worlds, life itself will rise, built from the scattered ashes of UY Scuti. Even here on Earth, the event will be unforgettable. While we are far enough away to be safe from the deadly radiation, the sight of such an explosion will become a once-in-human history event. Ancient civilizations recorded supernovae they could see in broad daylight, and those were from stars much smaller than UY Scuti. This one will dwarf them all. For a year or more, the glow will remain visible without telescopes, gradually dimming as radioactive elements forged in the blast decay and release energy into the expanding cloud. The brightest phase will fade, but astronomers will continue to watch its remnants for centuries, tracing the shockwaves and studying the elements it leaves behind. But for all its brilliance, the supernova is not UY Scuti's final word. Beneath the chaos, its core will have transformed into something new. Depending on its exact mass, it may settle into a neutron star, a city-sized object spinning hundreds of times per second, with magnetic fields strong enough to strip electrons from atoms miles away. Or if its mass tips beyond the threshold of stability, the core will collapse into a black hole, swallowing its own light and creating a void in space from which nothing can return. In either case, the firestorm of UY Scuti's death is not an end, but a transformation, a violent reshaping of matter and energy into forms that will ripple across the galaxy for billions of years. The spectacle of the supernova is both terrifying and beautiful. It is the end of a monster, yes, but also the source of creation. The same explosion that would annihilate anything in its immediate path will spread the ingredients of life across the stars. The same fire that destroys also forges, ensuring that UY Scuti's legacy will live on, not in its light, but in the countless worlds and beings that may one day emerge from its ashes. For the universe, destruction is never final. It is simply the beginning of something new. When the firestorm of UY Scuti's supernova finally subsides, the galaxy will be left with a haunting question: what remains at the heart of the destruction? For ordinary stars, the aftermath is simple. They shrink into white dwarfs, fading embers that cool silently over billions of years. But for titans like UY Scuti, the finale is far stranger and far more terrifying. The fate of this leviathan's core depends entirely on its final mass after the explosion, and both possible outcomes are beyond anything the human mind is prepared to comprehend. If UY Scuti's core shrinks to less than about 3 times the mass of our Sun, the result will be a neutron star, an object so bizarre it seems like science fiction. Imagine compressing the Sun into something no bigger than Manhattan Island. The resulting object would have a density so extreme that a single teaspoon of its matter would weigh more than Mount Everest. On its surface, gravity would be 200 billion times stronger than Earth's. A pebble dropped from a meter above the ground would hit with the force of an atomic bomb. The star would spin hundreds of times per second, faster than a helicopter blade, whipping up magnetic fields so strong that they warp atoms and tear particles from space. From Earth, such an object would appear as a pulsar, sending lighthouse-like beams of energy across the galaxy with clockwork precision, more accurate than any human-made atomic clock. To witness a neutron star is to see matter in its strangest form, atomic nuclei crushed into a single vast nucleus, a star transformed into a cosmic riddle made of neutrons packed shoulder to shoulder. But if UY Scuti's core weighs even slightly more than 3 solar masses, then not even neutron pressure, the last resistance of atomic structure, can hold back gravity. In that case, the collapse continues, shrinking matter beyond recognition, crushing it into something infinitely dense. At this point, the universe itself seems to break down, because physics cannot describe what happens inside. The result is a black hole, an object so extreme that not even light, the fastest thing in existence, can escape its grip. Around it forms the event horizon, an invisible boundary where time and space themselves are warped beyond recognition. To an outside observer, anything falling in appears to slow down, freeze, and fade into darkness, but to the object itself, the fall is swift, unstoppable, and final. A black hole left behind by UY Scuti would not be an ordinary one. It could weigh 20 or more times the mass of our Sun, a cosmic predator lurking silently in the debris of the explosion. Its gravity would bend light, distort space, and feed on whatever matter strayed too close, forming an accretion disk of superheated gas that glows brighter than entire galaxies. The energy released in this process is so enormous that it can outshine every star in its host galaxy. To encounter such a monster up close would be instant annihilation, torn apart by tidal forces in a process scientists grimly call spaghettification. And then there is the most extreme possibility of all. If UY Scuti is rotating rapidly, when its core collapses into a black hole, the result may not just be a supernova, but a hypernova, one of the most violent explosions in the known universe. Hypernovas create gamma-ray bursts, beams of energy so focused and so powerful that they release more energy in 10 seconds than our Sun will produce in its entire 10 billion year lifetime. These cosmic laser beams, narrow cones of destruction traveling at nearly the speed of light, are capable of sterilizing entire planets across thousands of light years if they happen to be in the path. Thankfully, UY Scuti is far enough from Earth and not oriented toward us in a way that makes such a burst a direct danger, but the sheer idea that the death of a single star could produce such a weapon of mass destruction is staggering. So whether it becomes a neutron star spinning like a cosmic lighthouse, or collapses into a black hole that swallows even light, or detonates in a hypernova that sends gamma rays piercing across the universe, the truth is this: UY Scuti's end will not be quiet. It will leave behind something alien, something monstrous, something that will serve as a permanent reminder of how fragile matter is when confronted with the raw power of gravity. What remains after its explosion will not be a star in any form we recognize. It will be a cosmic ghost, an object born of death that continues to haunt the galaxy long after the fire has faded. The death of UY Scuti may be distant enough to spare Earth from its full wrath, but the universe is not short on nearby ticking time bombs, and the dangers posed by massive stellar explosions are more than just distant curiosities. Within a few hundred light-years of our solar system, several stars are already nearing the end of their lives, each one a potential threat capable of reshaping life on Earth in ways both subtle and catastrophic. When massive stars die, they do not simply collapse into silence. They unleash radiation shockwaves and cosmic rays across the galaxy, and if one of these events occurred close enough, our world could feel the effects directly. The danger zone for such an event is roughly 50 to 100 light-years. Any supernova within this distance could potentially damage Earth's atmosphere, strip away the protective ozone layer, and expose the surface to deadly levels of ultraviolet radiation from the Sun. The consequences would be immediate and severe: massive die-offs in ecosystems, agricultural collapse, and widespread mutations that could reshape the course of evolution. It is not just theoretical. Some scientists believe mass extinctions in Earth's distant past may have been triggered by nearby supernovae or gamma-ray bursts, cosmic assassins striking invisibly from across space. One of the most famous candidates for such a future event is Betelgeuse, the red supergiant that marks the shoulder of Orion in the night sky. Betelgeuse has already entered its death spiral, pulsating and shedding material into space in a way that mirrors UY Scuti on a smaller but still dangerous scale. At just over 600 light-years away, Betelgeuse is too far to pose an existential threat. But when it finally explodes, and it could happen any time in the next 100,000 years, it will dominate our sky in a display unlike anything humans have ever witnessed. For months it will shine as brightly as the full moon, visible even during the day, a reminder that the stars we take for granted are not eternal. Its explosion will be harmless to us in terms of radiation, but psychologically it will shake civilization with the undeniable truth that the heavens are alive with violence. Other nearby stars are more worrisome. Systems like Ik Pegasi, located just 150 light-years away, contain white dwarfs that are stealing matter from companions. When these stellar corpses grow heavy enough, they can ignite in thermonuclear fury as type Y supernovae, events so luminous and destructive that they can briefly rival entire galaxies. If such a detonation occurred too close to Earth, it could devastate the ozone layer and trigger global climate collapse. Then there are Wolf-Rayet stars, stripped-down, ultra-hot giants that are prime candidates for gamma-ray bursts when they die. One such star, WR104, sits about 8,000 light-years away. While that distance is considered safe, astronomers cannot ignore the possibility that its eventual death could produce a burst aligned with Earth. A gamma-ray burst doesn't need to be near to cause trouble. Its beams are so focused and so energetic that even thousands of light-years may not be enough to fully shield us from its effects. If one were pointed directly at us, the consequences would be apocalyptic. The ozone layer stripped in seconds, ultraviolet radiation sterilizing the surface, and climate upheavals that could collapse ecosystems worldwide. But perhaps the most sobering truth is that many potential threats remain hidden. Stars nearing the end of their lives often shroud themselves in dust, masking their instability from our telescopes. Runaway stars, flung from their birthplaces at hundreds of kilometers per second, drift silently through the galaxy, some destined to explode close to systems like ours without warning. And while astronomers monitor the skies with ever-improving tools, the Milky Way is vast, containing billions of stars, most of them uncharted. Somewhere out there, unseen by human eyes, another giant may already be counting down the final moments to its death, preparing an explosion that will echo across the galaxy. For now, Earth is safe. The ticking bombs nearest to us are either too far away or not yet ready to blow. But cosmic time is patient. In the long run, it is not a question of if a nearby supernova or gamma-ray burst will affect Earth, but when. The universe has been detonating these stellar bombs for over 13 billion years, and our planet has existed for only a fraction of that span. The odds say we will one day feel their touch again. Whether it is through mass extinctions, climate disruptions, or subtle changes to our evolutionary path, the cosmos reminds us with every dying star that our world is fragile, shielded only by distance and chance from forces far beyond our control. The death of UY Scuti may be distant enough to spare Earth from its full wrath, but the universe is not short on nearby ticking time bombs, and the dangers posed by massive stellar explosions are more than just distant curiosities. Within a few hundred light-years of our solar system, several stars are already nearing the end of their lives, each one a potential threat capable of reshaping life on Earth in ways both subtle and catastrophic. When massive stars die, they do not simply collapse into silence. They unleash radiation, shockwaves, and cosmic rays across the galaxy. And if one of these events occurred close enough, our world could feel the effects directly. The danger zone for such an event is roughly 50 to 100 light-years. Any supernova within this distance could potentially damage Earth's atmosphere, strip away the protective ozone layer, and expose the surface to deadly levels of ultraviolet radiation from the sun. The consequences would be immediate and severe: massive die-offs in ecosystems, agricultural collapse, and widespread mutations that could reshape the course of evolution. It is not just theoretical. Some scientists believe mass extinctions in Earth's distant past may have been triggered by nearby supernovae or gamma-ray bursts, cosmic assassins striking invisibly from across space. One of the most famous candidates for such a future event is Betelgeuse, the red supergiant that marks the shoulder of Orion in the night sky. Betelgeuse has already entered its death spiral, pulsating and shedding material into space in a way that mirrors UY Scuti on a smaller but still dangerous scale. At just over 600 light-years away, Betelgeuse is too far to pose an existential threat. But when it finally explodes, and it could happen any time in the next 100,000 years, it will dominate our sky in a display unlike anything humans have ever witnessed. For months, it will shine as brightly as the full moon, visible even during the day, a reminder that the stars we take for granted are not eternal. Its explosion will be harmless to us in terms of radiation, but psychologically it will shake civilization with the undeniable truth that the heavens are alive with violence. Other nearby stars are more worrisome. Systems like Ik Pegasi, located just 150 light-years away, contain white dwarfs that are stealing matter from companions. When these stellar corpses grow heavy enough, they can ignite in thermonuclear fury as type Ia supernovae, events so luminous and destructive that they can briefly rival entire galaxies. If such a detonation occurred too close to Earth, it could devastate the ozone layer and trigger global climate collapse. Then there are Wolf-Rayet stars, stripped-down ultra-hot giants that are prime candidates for gamma-ray bursts when they die. One such star, WR104, sits about 8,000 light-years away. While that distance is considered safe, astronomers cannot ignore the possibility that its eventual death could produce a burst aligned with Earth. A gamma-ray burst doesn't need to be near to cause trouble. Its beams are so focused and so energetic that even thousands of light-years may not be enough to fully shield us from its effects. If one were pointed directly at us, the consequences would be apocalyptic. The ozone layer stripped in seconds, ultraviolet radiation sterilizing the surface, and climate upheavals that could collapse ecosystems worldwide. But perhaps the most sobering truth is that many potential threats remain hidden. Stars nearing the end of their lives often shroud themselves in dust, masking their instability from our telescopes. Runaway stars, flung from their birthplaces at hundreds of kilometers per second, drift silently through the galaxy, some destined to explode close to systems like ours without warning. And while astronomers monitor the skies with ever-improving tools, the Milky Way is vast, containing billions of stars, most of them uncharted. Somewhere out there, unseen by human eyes, another giant may already be counting down the final moments to its death, preparing an explosion that will echo across the galaxy. For now, Earth is safe. The ticking bombs nearest to us are either too far away or not yet ready to blow. But cosmic time is patient. In the long run, it is not a question of if a nearby supernova or gamma-ray burst will affect Earth, but when. The universe has been detonating these stellar bombs for over 13 billion years, and our planet has existed for only a fraction of that span. The odds say we will one day feel their touch again, whether it is through mass extinctions, climate disruptions, or subtle changes to our evolutionary path. The cosmos reminds us with every dying star that our world is fragile, shielded only by distance and chance from forces far beyond our control. Would you like me to continue with Section 8, the cosmic cycle, how UY Scuti's death and others like it seed the galaxy with the elements for new stars, planets, and life, in the same flowing style? You said, start with Section 8. No segmentation, not less than 500 words. ChatGPT said. Here's Section 8, written as a single flowing narrative with no segmentation and over 500 words, keeping it cinematic and engaging for maximum retention. The death of UY Scuti will not only be a spectacle of destruction, but also a profound act of creation. In the violence of its final moments, this red giant will scatter its essence across the cosmos, and from those ashes, new stars, new worlds, and perhaps even new forms of life will one day emerge. It is a cycle as old as the universe itself. Stars live fast, burn bright, die violently, and leave behind the raw materials that seed the next generation. Without this process, there would be no planets, no oceans, no biology, and no humanity to look up at the sky in wonder. Everything we are is built from the corpses of ancient stars. The carbon in our cells, the oxygen we breathe, the calcium in our bones, the iron in our blood, all of it was forged in stellar furnaces and spread across space by supernovae. UY Scuti's end will be one more link in this endless cosmic chain. When its core finally collapses and its outer layers are blasted into the void, the explosion will scatter more than 20 times the mass of our Sun into interstellar space. That debris will carry with it a rich cocktail of elements: carbon from helium fusion, oxygen from carbon burning, silicon from oxygen fusion, iron from silicon burning, and heavier elements forged in the explosive violence itself. These atoms will drift outward for thousands of years, merging with clouds of gas and dust that already swirl between the stars. Over time, the shockwave will compress parts of those clouds, triggering new bursts of star formation. In this way, UY Scuti's death will directly sow the seeds of stellar nurseries, vast regions glowing with the light of newborn stars. Some of those stars will form planetary systems. Some of those planets will be rocky, built from the very silicon and iron created in UY Scuti's core. And on one of those planets, perhaps billions of years from now, chemistry may spark into biology, and biology into consciousness, repeating the story of life in an endless cycle of renewal. This recycling is not unique to UY Scuti, but is the engine of cosmic evolution. In the beginning, after the Big Bang, the universe contained only hydrogen and helium, the simplest elements. The first stars were massive and short-lived, burning their fuel and exploding in primordial supernovae that enriched the void with heavier atoms. Each generation of stars added more complexity, more building blocks for worlds. By the time our Sun formed, about 4.5 billion years ago, the galaxy was already rich with carbon, oxygen, silicon, and iron, allowing planets like Earth to emerge. In a sense, we are second-generation beings, assembled from the remnants of stars that lived and died long before us. UY Scuti is part of that same process, a future ancestor to planets and life forms that do not yet exist. The explosion will also create elements that could never form in ordinary stars. In the furnace of the supernova, rapid neutron capture will forge gold, platinum, uranium, and other heavy metals, scattering them across light years of space. These atoms will eventually become embedded in asteroids, melted into planetary crusts, or locked within the cores of distant worlds. Every piece of gold on Earth, every coin, every crown, every ring, is a gift from a star's death. When UY Scuti detonates, it will create riches beyond imagining, but not for us. They will belong to the stars and planets that have yet to be born. What makes this cycle so powerful is that it is unending. Destruction is never final in the universe. It is transformation. A star's death is violent, but the chaos gives rise to order, to the possibility of life and complexity. UY Scuti may seem like a monster, a bloated red giant on the brink of collapse, but in truth it is a giver. Its death will ensure that the galaxy remains fertile, its elements scattered like seeds across the cosmic soil. Long after its light fades from our skies, its atoms will endure, drifting silently until gravity gathers them into something new. That is the legacy of stars, not their ruinous in life, but their generosity in death. When we look at UY Scuti, we are not just seeing a star, we are staring into a cosmic paradox, a being both terrifying in its scale and beautiful in its purpose. It is the largest known star in our galaxy, so swollen that if it replaced our Sun, it would consume Earth, Mars, and much of the asteroid belt in its fiery body. It pulses with a heartbeat that takes years to complete, a rhythm of expansion and contraction that is the soundless ticking of a countdown clock. And yet, for all its enormity, UY Scuti is fragile, burning through its life at reckless speed, unable to endure for billions of years, like our calm and steady Sun. It is a giant racing toward an inevitable end, one that will arrive in violence, with an explosion so powerful it will briefly outshine every other star in the Milky Way. Its life is short, its death inevitable, but its legacy eternal. The story of UY Scuti reminds us that the universe is not static. What looks eternal to our eyes is in reality fleeting, a dance of creation and destruction that has been going on for over 13 billion years. Every star is born from the ashes of those that came before. Every planet forged from dust, scattered by explosions like the one UY Scuti will unleash. Even we, fragile beings on a small blue world, are participants in this cycle. The iron coursing through our blood, the oxygen filling our lungs, the calcium in our bones, all of it was created in ancient stars that lived, died, and exploded long before our Sun was even born. We are literally made of stardust, children of cataclysms, proof that destruction is not the end, but a transformation into something new. UY Scuti will one day join that cycle, and its death will ensure that countless stars and planets yet unborn will carry pieces of it within them. But this is not just a story of cosmic recycling. It is a story about power, fragility, and perspective. UY Scuti dwarfs our Sun, yet it burns so fast that its entire lifetime is measured in millions of years. A blink compared to the billions our Sun will last. Its size does not grant it immortality. In fact, it seals its doom. The very thing that makes it so magnificent is also the reason it cannot survive. That contradiction is the truth of the universe. Everything that shines brightest also burns the fastest. For UY Scuti, there is no gentle fade into obscurity. Its end will be sudden, violent, and final. And yet, even in its destruction, there is wonder. When it explodes, the night sky will be changed. For a time, humans on Earth may look up and see a second sun glowing in the heavens, casting shadows in the day and dominating the night. Astronomers will study it, civilizations will marvel at it, and poets will write of the day the heavens burned. Long after its light fades, its legacy will remain in the atoms scattered across the galaxy. Somewhere in the far future, a planet may form from those atoms, a world with oceans and mountains, skies and storms, perhaps even life. And if intelligent beings arise there, they will be built, in part from UY Scuti itself, living echoes of a star that died billions of years earlier. The death of UY Scuti is not the end of a star. It is the continuation of a cycle that never stops. In the universe, endings are beginnings, and destruction is creation. To witness a star's death is to glimpse the deepest truth of the cosmos, that even the most violent forces serve a purpose. UY Scuti will collapse. It will explode. It may leave behind a neutron star or a black hole, but what it truly leaves behind is far greater. It will give the galaxy new life, new stars, new planets, and new possibilities. Its brilliance is temporary, but its gift is eternal. So when we think of UY Scuti, we should not see only a monster waiting to die. We should see a cosmic gardener preparing to scatter its seeds across the galaxy. Its light will one day vanish, but its atoms will endure, carried into the future by gravity and time. From those fragments, new worlds will form. And perhaps one day, new eyes will look up at their sky, wondering where they came from. never knowing that they are the children of a red giant that once blazed in Scutum. In the end, UY Scuti is not just the largest star we know. It is a reminder that even in death, the universe creates, and that everything from the stars above to the life within us is part of the same eternal story.